So basically this week is about resolving some forces into components. Their example in the book, resolving a force, say you're dragging a book. The most effective way to drag a book along the tabletop is surely to drag it in the direction that it's going to end up moving, right? So horizontally. Usually, if you drag a book along a tabletop, some of your effort is going vertically as well. And basically, we're going to use trigonometry to divide up how much of your effort or force is going this way or that way, so that we can do sums with that, do maths to find out certain results. For example, how much of your force is having the effect you want in this direction here? All of it. Supposing you're cycling along this blue dotted line here, supposing that's you cycling along and we're looking down. We are birds looking down on you cycling along that blue dotted line, and the red line is the wind. Right? Now the wind, therefore, is blowing you sideways, isn't it? Do you see what I mean? The wind is blowing you sideways. The blue dotted line is you or somebody or me cycling along in that direction, and we're looking down. We are pigeons, perhaps, that's me cycling along, but what we can see here is the pigeon's eye view. Maybe I'm about to get dropped on by the pigeon.
So okay. Where are the pigeons?
We are the pigeons looking down. This is a bird's eye view, we call it. We're looking down, and we can see a cyclist moving along there. Now, from this bird's eye view, what's the effect of the wind blowing the cyclist there? Is it going to be helping the cyclist to go forwards, or is it going to be blowing the cyclist backwards at all? Is the wind helping or not helping the cyclist to go forwards?
But the wind is the wind upwards? Or?
No, good point. We are talking about a bird's eye view. We're saying that's forwards, that's sideways. We're looking down on a map. Think of this as a map. Maybe that's north, maybe that's east. Yeah, the cyclist is traveling east, and the wind is blowing north. Yeah. Hopefully that does clarify it. Yeah, the wind is blowing north.
Oh.
The cyclist is traveling east.
Yeah.
So what's the effect of the wind on the cyclist?
Not helping.
Not helping? I agree, it's certainly not helping. Is it being positively unhelpful and dragging the cyclist backwards? No, not that either. I agree. Yeah. I mean, you might say maybe I'll fall over. Maybe it's blowing me off balance. And that might be true. But as far as my progress east goes, it's not helping me go east. It's not dragging me back west either. And that's because it's at right angles to the direction we're looking in. So when we decompose a force vector, we're saying let's decompose or resolve a force. We might say pulling this hard, the length of the arrow there is representing the strength of the force, may be the same as pulling that hard in that direction together with that hard in that direction. You might say, I'd rather pull that direction and then I don't need to pull so hard. That's true. If you have two people pulling this way and that way, they're wasting some of their energy. But to look at it another way, a force pulling this way, we could regard it as having an effect of that magnitude in that direction and another effect there. But it's never going to have any effect if I just fix the direction. Yeah, I'll fix the right angle there. Okay, so this is our force. How much of this force is pointing this way? That much. How much is pointing that way? That much. But suppose we go at right angles to the force now. Notice how, as we approach right angles to this force, less and less of it is having any effect. In their first example, they were saying, what if, how much of it is pointing in the direction of the force? All of it. If we have all of that in the right direction, then it's going to be times 1. That's what they said back here, in this direction here. The amount in this direction is going to be all of it, times 1. All right? But how much of it now is pointing this way? Less of it. And as we get closer to being at right angles, you know, as this one gets closer to being parallel, the other one is getting closer to being at right angles. It's getting titchy, so it's kind of disappearing. But that's because the magnitude is disappearing. So if you've got a force and it's pointing in a particular direction, we can resolve it or decompose it into 2 or more, but usually 2 different directions. And none of it is going to be pointing at right angles. None of it is going at right angles. All of it is going straight ahead, of course. I think their third example is how much of it is pointing backwards. I'm not sure if this thing could cope with that. No, not going more than 90 degrees. But here it wants to say that how much of this force is pointing east. Well, this is like a wind blowing the cyclist exactly backwards, isn't it? So we would say the force in the direction of the cyclist here is precisely the negative of the force. You know, it's being completely unhelpful, driving it back west. Okay? Or not? A bit. Okay? It's your first encounter possibly with trying to think of how much of a force is pointing in a particular direction. And then they're inviting us here, say, how much of this force is pointing in the easterly direction. Now, I don't know if you're familiar with the I and J notation, not that I. That I means question part 1, okay? But this I here is saying how much of a force is pointing in east direction. I means east, J means north. So I means X really, because X is east and Y is north, isn't it? All right. And so here they're saying, well, find out how much of this force is pointing in the I direction and call that P. Find a number for P, the amount of this pointing in the X direction. And you can see that the trigonometry to do there, look at this force vector here. How much is pointing east? We can think of it like that. Now we can do some trigonometry, can't we? Here's the string that's actually pulling. It's like a string pulling that hard in that direction and that hard in that direction. And they want to know how hard in each direction. I means east, J means north, I means X, J means Y. So how much is pulling here? Well, what's the trigonometry going to be? If you look at one of these right-angled triangles and you say you've got 9 here, that's 9. What are these components of it here? So if this is 40 degrees, isn't it, here?
40 equals to 9 divided by cosine 40.
Cos 40 times 9.
Divided or times?
Times.
Yeah. Cos 40 is generally telling us what this is as a proportion of the hypotenuse, isn't it? So you can say to yourself, yes, of course, in general, the adjacent is going to be this fraction, the cos 40 fraction of the hypotenuse, which is 9. So we want the cos 40 fraction of 9. Does that make sense? What does cos 40 mean? It means the adjacent as a fraction of the hypotenuse. So let's have that fraction of 9 in this case. So we'll call it cos 40 times 9 or 9 cos 40. And then similarly, what does sine mean? It means the vertical part of this, doesn't it? The sine of 40 is telling us the vertical fraction of 9. So we would say 9 sine 40 and put that there. You would like to find out what that is as a number? Go ahead, John. Put it in your calculator. 9 cos 40. Only 6. Ah, because have they underestimated? I don't know. So are you sure you're in degrees? What are you getting? Go on then.
Seems.
Okay. All right. Well, that's just my problem then. If I thought that seemed too small, because I haven't, maybe they've drawn 40. It does look rather like 30 degrees, doesn't it? They're 40 degrees. So that would tend to explain. If I remove that, if we make it a bit more like a realistic 40, then that looks a bit more like 6 point something, yes. Fair enough. So there was some point in doing this, yes. Fine. How do you put your answer in that form there? They're saying, please give your answer in that form. So your answer should be 6.9i plus how much j is how you'll do it. Where people know that the I vector is one unit of force pointing in the easterly direction. And the j vector is one unit of force pointing in the north direction. So the answer to your question is 6.9i plus however much j, and you would be guessing how much? Take a guess at how much j. I'm thinking if that's 9, and now I can believe that that's 6.9, or 6 point anything.
4.2 approximately.
4?
4
root 2. Well, that's exact then, rather than approximate, which is fine. Yeah?
Approximately, because for me,
I see.
It's not 6.9, I put 7. So, and after you do the Thales theorem,
Pythagoras theorem.
Pythagoras, you're using Pythagoras, so you're thinking this ought to be the square root of 81 minus 6.9 squared. Yeah? And you did that up here. And you're getting what?
81 minus 49.
Ish. I like it. Is?
32.
32. Root 32.
Root 32, we know that it's 8 times 4, so it's...
So 2
yes.
root 8. And which is 4 root 2.
Yes.
Oh, right. Now I see where your root's coming from.
Yes.
And that's great. So what we've got here is 9 cos 40, which turned out to be approximately 6.9. And then what we've got here is 9 sine 40, the sine 40 fraction of 9, the hypotenuse. And why is it the sine 40 fraction? Because what does sine mean? That vertical there as a proportion of the hypotenuse, opposite over hypotenuse. But Arno's idea was delightful, that we say it's got to be the square root of 81, which is 9 squared. So we're using Pythagoras and saying 9 squared minus 6.9 squared. And 6.9 is virtually 7, so we're estimating approximately equal to 81 minus 49, 32, root 32.
Or
if you think of it as root 16 times 2, is that fair enough?
Right.
So hence 4 root 2, because you've got root 16 times root 2, which is 4 root 2, okay? Shall we see whether 4 root 2 is impressively close to 9 sine 40? So who's got the calculator? Would you please do 9 sine 40? 5.79-ish. And 4 root 2-ish?
is 5.42 is 5.66.
5.66. So very impressively close from Arno's idea of doing Pythagoras there. So what we get is, for part A, this much I, and you'd put a little underline there to show that you're making it bold. That I is bold to indicate that it's a vector. It's what we call a unit vector. I is a unit vector in the easterly direction, so it needs to be underlined to show that you would do it bold. The thing with vectors, if you notice, you need a way of indicating that you're talking about a vector, but what you don't want to do is to try and make it noticeably bolder than your other. You might think I didn't do too badly there, but you can see it's going to be pretty messy. Your work is going to be messy if you try and make your handwriting bold like printing is bold. So we use this convention, and you would say 6.9i plus this much, 5.79j.
Can we put like an arrow to J, or I don't know?
You would rather I put an arrow there?
I don't know, that's what we do.
Sometimes we indicate a vector with arrows whereby we say what you're probably thinking of. We could talk about the vector that's called, and you'd write it as A to B like that.
Yeah, but even with like J.
Well, if you were going to, you would do it like this, wouldn't you? You'd say it's from the point 0, 0, the origin, to the point where? Oh, is it I or J? I suppose if this is I ought to make clear. I is the vector which takes you from the origin to one along the horizontal axis, but nowhere up. Bear in mind, though, it doesn't have to be that, because when you use this arrow notation, you can start anywhere as long as you go the right distance in the right direction. So it could be 3, 4, taking you to where? 4, 4, well done. Yeah. So that's I, if you want to know what I is. It's either of those, because it doesn't matter where you start or finish as long as you go the right distance in the right direction. And the distance is 1 unit for these so-called unit vectors I and j. So there's your answer. Okay. So moving on to